Next, condensers. Mga types na. For the condensers, the fluid to which heat is ejected is usually either air or water. Pwedeng sa air, pwedeng sa water. Another type of water-cooled condenser has cleanable tubes. Figure 10. Cleanables, pwede mo siyang open na open sa pinilinisan. When the condenser is water-cooled, the water is sent to the cooling tower for ultimate rejection of the heat to the atmosphere. Doon naman siya magano sa cooling tower kasi remote. Some years ago, air-cooled condensers were used only in a small refrigeration system, less than 100 kilowatt refrigerating capacity. Yung mga split type natin na aircon, di ba? But now, individual air-cooled condensers are manufactured in sizes matching refrigeration capacities of hundreds of kilowatt. The water-cooled condenser naman is favored over the air-cooled condenser where there is a long distance between the compressor and the point where heat is to be rejected. Yan ang option. Yan ang consideration ng cooling tower. Kasi alangan namang refrigerant ang ilagay mo sa piping na ang layo-layo. Okay? Most designers prefer to convey water rather than refrigerant in long lines. Yan nga. In centrifugal compressor systems, large pipes are needed for the low-density refrigerants so that the compressor is close coupled to the condenser. Water-cooled condenser, therefore, predominant in centrifugal compressor system. So, ito yung water-cooled condenser with cleanable tubes. Apat yan, kala nyo. Yung isa dyan, isa. So, wala itong pins. So, ibang klaseng ano to, tube in tube yan. Okay? Then sa i-transfer nyo, makikita nyo yung mga tube in tube doon. So, the required condensing capacity. So, the required rate of heat transfer in the condenser is predominantly a function of refrigerating capacity and the temperature of evaporation and condensation. The condenser must reject heat, both the energy absorbed by the evaporator and the heat of compression added by the compressor. That is, condenser is equal to evaporator plus the compressor. A term often used to relate the rate of heat flow at the condenser to that of the evaporator is the heat rejection ratio. It is the ratio of rate of heat rejected at condenser divided by the rate of heat absorbed at the evaporator. Yan. Kaya ang tawag doon is heat rejection ratio. Ginagamit yun pag may mga sa nag-graphical yung ano mo, calculation. So ito. Theoretical calculation of the condenser heat rejection can be made from the standard vapor compression cycle, but they do not take into consideration the additional heat added by inefficiencies in the compressor. A graph of typical values of heat rejection ratio is shown on figure 1.1. So ito, pwede mo na itong maging basis kung ang ano mo, ang refrigerant mo is 12 and 22. Yan. For type of compressor, andito. Negative 10 evaporator, 0, negative, and 10C. So, ano yung condensing mo? So, makikita mo dito yung heat rejection ratio. So, pag na-compute mo yung ilang kilowatt yung evaporator, multiply mo lang, yun na yung heat sa condenser mo. Okay? When the motor driving the compressor is hermetically sealed, some of the heat associated with inefficiencies of the electric motor is added to the refrigerant stream and must ultimately be removed at the condenser. So, the heat rejection ratios of the hermetically sealed compressor are usually slightly higher than those of the open type compressor. Yan ang dahilan yan. Next is the condensing coefficient sa evaporator, and ito applicable to dun sa condenser. Anong nagko-condense doon? Yung refrigerant mo, kinocondense mo. So ito sa refrigerant. Kanina is sa fluid, sa water. So the basic equation for calculating the local coefficient of heat transfer of vapor condensing on a vertical plate was developed by Nusselt by pure physical analysis. Ito, figure 12. So the equation for the local condensing tayo, coefficient is in the evaporation. H sub CB times X over K is equal to G rho squared times H sub FG X cube over 4 mu K delta T is 0.14. Where H sub CB is the local condensing coefficient on vertical plate, X vertical distance measured from the top of the plate, and G is the acceleration due to gravity, 9.81 meter per second squared. Rho is the density of condensate. S sub FG, condensate, yung vapor. S sub FG is the latent heat of vaporization. Mu is the viscosity of the condensate. Delta T, temperature difference between the vapor and the plate, yung surface temperature. So now the mean condensing coefficient over the total height of the plate L is H sub CB bar is equal to the integral of H sub CB dx from 0 to L over L. Ang value is 0.943 times G rho squared H sub FG K cube over mu delta T L is 0.14 watts per meter squared Kelvin. So depende sa units. So the equation for the mean condensing coefficient for vapor condensing on the outside of horizontal tubes naman, H sub CT is equal to 0.725 times G rho squared H sub FG K cube over mu delta T and D. So where N, number of tubes in vertical row, D is equal to OD of tube meters. Yan. So dinerive natin yung vertical, then lumabas din yung horizontal. So deprivation nito, check nyo na lang doon sa mga heat transfer book. Several investigators have found that the constant 0.725 in equation 24 agrees closely with experimental result. White found the constant to be 0.63 and Goto et al. Found it to be approximately 0.65. Okay. So yun yung condensing coefficient sa condensing vapor. The next, fouling factor. So pag hindi siya clean, ang design tayo is para sa clean tubes. So yung hindi lahat ng tubes na bibili mo is malinis. So consider natin yung fouling factor. After a water-cooled condenser has been in service for some time, its U value usually degrades somewhat because of increased resistance to heat transfer on water side due to fouling by impurities in the water from the cooling tower. Pinabanggit dito is yung sa water side. The new condenser must therefore have a higher U value in anticipation of the reduction that will occur in service. The higher capacity with new equipment is provided by specifying a fouling factor 1 over HFF, meter squared Kelvin per watt. This term expands equation 8 for U value into 1 over U sub O is equal to 1 over H sub O plus X H sub A O over K A sub M plus A sub O H sub FF EI plus A sub O H sub I H sub I. Ito yung equation 8 dun sa yung evaporator naman yung pins. So, nakatabi yung SF mo sa A sub I kasi nga sabi dito water. Okay? Several different agencies have established standard for the fouling factors to be used. So, hindi tsamba-tsamba, may standard na sinusunod. One trade association specifies 0.000176 meter squared Kelvin watt per Kelvin per watt. Which means that the condenser should leave the factory with 1 over U value of 0.00176 A sub O also A sub I less than the minimum required to meet the coated capacity of the condenser. Ayusin natin to. The superheating. So even when the refrigerant condenses at a constant pressure, its temperature is constant only in the condensing portion. Diba sa saturation TS diagram natin, nakita natin to. Yan. So, ditong side, ito yung curve, saturation curve. So, dito siya pumapasok. So, magkakaroon muna siya ng superheating, then condensation, then subcooling. Yan, ibig sabihin niya. Because the vapor coming from the compressor is usually superheated, the distribution of temperature will be as shown in figure 13. So, anong purpose to ba't ina-explain? Andito. Because of the distortion in the temperature profile caused by the operating process, the temperature difference between the refrigerant and the cooling fluid is no longer correctly represented by LMTD. LMTD is equal to TC minus TI. Yung mga temp saturation to minus TC minus TI over ln of TC minus TI over TC minus TO. So now, equation 26. It is common practice to use equation 26 anyway with the following justification. Although the temperature difference between refrigerant and cooling fluid is higher in the operating section than calculated from equation 26, the convection coefficient indication is normally lower than the condensing coefficient. The two errors compensate somewhat for each other, and the application of equation 26 along with the condensing coefficient over the entire condenser area usually provides reasonable accuracy. So allowed pa rin to. Okay? Explain lang. Condenser design. Tayo ng design. Example din sa libro to. Explain na natin. An example will illustrate how some of principles described in the previous section are combined in designing a condenser. Yan. Describe natin. The condensing area is to be, example number 3. The condensing area is to be specified for a refrigerant 22 condenser of a refrigerating system that provides a capacity of 80 kilowatts for air conditioning. The evaporating temperature is 5C and the condensing temperature is 45C at design condition. Water from a cooling tower enters the condenser at 30C and leaves at 35C. Yeah. The two-pass condenser with 32 tubes arranged as shown in figure 14 will be used, and the length of the tube is to be specified to provide the necessary area. The tubes are copper and are 14 mm ID and 16 mm OD. So wait itong 154 pampalgulo. So given refrigerant 22, 80 kilowatt refrigerating capacity, 5C evaporating temperature, 45C condensing temperature, 30C to 35C water. Two-pass condenser with 42 tube as shown. So this is a two-pass. So mahati yan. ID 14 mm, OD 16 mm. Required area and tube length. Ito ang kailangan natin sa design ng heat exchanger. Solution. Calculate the required rate of heat transfer, the individual heat transfer coefficient, and the overall heat transfer coefficient. Then compute the required area of and tube length. So, unahin natin yung rate of heat transfer. From figure 11, assuming the compressor to be hermetic one, the heat rejection ratio at the condensing temperature of 45C and the evaporating temperature of 5C is 1.27. Kasi given yung mo, evaporate, ito, refrigerating capacity mo is 80 kilowatt. Paano makuha yung sa condenser? Yan. So, given nyo for 5C and 45, tapos 5C, so hanapin mo dito yung value. Ito siya, di ba? Between dyan, 0, ano yon? Open, hermetic one. So, hermetic. So, dito ka gitna. Yan, gitna nito, hermetic one. 5, 0, 10. So, yan. This is 1.26. 27. So, condensing the 45 and 5. So, yan. 45. Tapos, napin mo yung 5 dyan. Nagtabingi yata. So, siya, 1.27. 1.25 to 26.27. So, natataas siya. Mali yung ano. Okay. So, itama niya lang. 25 tapos 5. Itong between yan 5. So, lalabas is 1.27. So, the rate of heat ejected at the condenser Q is equal to 80 times 1.27 is 101.6. Yan. Now, for the condensing coefficient from equation 24, S of condenser is 0.725. Kasi horizontal siya, di ba? Times, ito yung equation mo, 0 squared S of FGK cube over mu, delta T, and D. So, the density law and the latent heat of vaporization, H of EB at 45 are available from tables. So, rho is equal to 1 over 0.9020 liters per kilogram is 1.109 kilogram per liter or 1109 kilogram per cubic meter. This is now, S of FG is 160,900 joules per kilogram. Okay. So the thermal conductivity and viscosity mu of the liquid refrigerant at 45 C are also available from tables. We have K is 0.0779 watts per meter Kelvin. Mu is equal to 0.000180 Pascal second. Consistent na yan. So ito nga yung graph. 45 dito yan. So kayo na magtali yan. Now, for N, ano yung N? The average number of tubes in vertical row is N is equal to 2 plus 3 plus 4. Plus yung average niya is 30.23. So, ito gamitin mo. So, the temperature difference between the vapor and the tube is unknown. At this point, so delta T will be assumed to be 5K. Yan, kasi may ina-assume dyan. So, ito yung realistic and the value adjusted later if necessary. Yan. So, ito yung delta T sa equation. So, H condenser is, substitute mo yung value, naging 0.725 times 9.81 times 1109 squared times 160,900 times 0.0779 cube over 0.000180 by 5 divided by 3.23 times 0.016 exponent 1/4. So, H condenser is 1520 watts per meter squared Kelvin. Now, for the metal, the copper to is 390 watts per meter Kelvin. And the resistance of the tube X E sub O over K S sub M is 0.016 minus 0.014 over 2 over 390 is equal to 6 times 16 over 14 plus 16 over 2. Ito, yung mean. Yan. This is now 0.00002735 meters squared Kelvin per watt. So, huwag kayong mag-lang. Okay. So, a value that will prove to be negligible in comparison with other resistance. Proven lang. Fouling factor is, section 10, 1 over h sub FF is 0.0000176. So, mas maliit pa rin to. So, manineglect talaga. So, water side coefficient. So, doon naman sa ano, yan nga yung equation natin. The flow rate of water needed to carry the heat away from the condenser with a temperature rise of 30 to 35 C is 101.6 kilowatt over 4.19 over 35 minus 30 is 4.85 kilogram per second. And the flow rate, divide mo siya ng density, which is 0.00485 cubic meter per second. Get the velocity is 0.00485 over 21 tubes per pass. Diba? Yung tubo mo is 42. So, kalahati nun, yung kung 21, andun papasok. Sa 21 tube, andun yung lalabas. Kaya, got 2 pass. Then 5 over 4, and 0.014 squared is equal to 1.5 meter per second. So, dito, ang diameter natin is 0.014 kasi inside siya. Nasa loob. Okay, ayan. Yung itong sa refrigerant, nasa labas siya, kaya ang outside diameter mo is yung OD. Equation 9 can be used to calculate the water side coefficient H sub W using the water properties at 32C. So the density is 995 kilogram per cubic meter. Cp is equal to 4190 joule per kilogram Kelvin. Nu is equal to 0.000770 Pascal second. K is equal to 0.617 watts per meter Kelvin. Okay? May mga ibang book na i-transfer na exact, alos ina-accurate nila yung value. Kasi tingin ng table. Kasi di lagi ang density ng water is 1,000. Okay? So then HD over K is equal to 0.023 times BD rho over mu times 0.8, 1.8 times CP mu K upon 0.4 substitute values. H of W is equal to 0.617 times 0.023 over 0.014 times 1.5 yung velocity meter per second times 0.014 995 divided by 0.000773 exponent 0.8 and multiply by 4190 times 0.000773 over 0.617 exponent 0.4. So the H of W is 6910 watts per meter squared Kelvin. Hindi ko na basahin to. Yan. So the required area now is 1 over U sub O is equal to 1 over H sub O plus X, A sub O over K, A sub M plus A sub O over H sub FF, A sub I plus A sub O over A sub I, A sub I. Based on outside area, is 1 over 1528 plus 0.00000275 plus 0.016 over 0.014. This is 1 over H sub FF, 0.000176 plus 0.016 over 0.014 times 1 over 690. Okay? Bakit area tapos relation natin yung diameter? Kasi yung area is pi times diameter times the length. So makakasir yung diameter, yung pi sa ka-length. Yan. So 1 over U sub is equal to 0.001023 or U sub is equal to 977 watts per meter squared Kelvin. So this is now the U value. Now the LMTD. LMTD, ito yung equation mo, TC minus TI minus TC minus TO over ln of TC minus TI over TC minus TO. LMTD is 45 minus 30 minus 45 minus 35 over ln of 45 minus 30 over 45 minus 35 is equal to 12.33 C. Now the area now is Q over U sub LMTD is equal to 101,600 over 977 over 12.33 is 8.43 square meter. So this is now the area, heat transferred area. Now the length of the tube, L is equal to 8.43 meters squared over 42 divided by 0.016 is 4.1 meters. So ang ano mo is, ang length ng ano mo, yung tubo is 4 meters plus yung sa headers mo, yung magiging length ng heat exchanger mo. At yung diameter naman ng shell, so pagkakasya, kung ano magkakasya doon sa 42 tubes. Gagawa ka ng drawing tapos pagka-sign anong spacing niya. So, gawa ka na lang. Makukuha mo yung shell diameter. A recheck should now be made of the assumption of 5K temperature difference used in calculating the condensing coefficient. So, a recalculation may be necessary. Yeah. The designer would also check the water pressure drop in the condenser to see that it does not exceed a reasonable value, perhaps of the order of 70 kilopascal. So sa mga graph, sa mga table ng catalog. So di na pinakita dito yung pagkuha ng pressure drop. Sa catalog na yan. So Wilson plot. Ang tawag dito is a Wilson plot to determine the individual heat transfer coefficient of a condensed compressor. So constructing a Wilson plot is a technique of processing heat transfer data to determine the individual heat transfer coefficient in a heat exchanger. This concept was introduced by Wilson and is often applied to condenser and evaporators to determine the condensing or evaporating heat transfer coefficient along with the air or water side coefficient. If it is a water-cooled condenser that is being analyzed, for example, a series of heat transfer tests is run and the U value determined for various flow rates of cooling water. If the condenser are clean, equation 8 applies and HO is the condensing side coefficient and HI is the water side coefficient. Ito yung equation niya. 1 of U sub O plus 1 of H sub O plus X to A sub O over K A sub M plus A sub O over HI A sub I. Nawala yung efficiency, nawala yung efficiency, wala rin yung Fouling factor kasi nga tawag dito is clean. Now, the properties of cooling water are primarily a function of temperature, and if the temperature range throughout the test is not large, the properties may be assumed constant. Equation 9 can then be simplified to h sub I is equal to constant times b exponent 0.8. The Wilson plot for this heat exchanger is a graph of 1 over u sub O versus 1 over b exponent 8. So, yan. Air and non-condensable. Ito yung mga naiiwan dun sa tubo. Mga space gap. If air or other non-condensable gases enter the refrigeration system, they will ultimately collect in the condenser, where foreign gases reduce the efficiency of the system for two reasons. One, the total pressure in the condenser is elevated, which requires more power for the compressor per unit refrigeration capacity. The condenser pressure is raised over the saturation pressure of the refrigerant by the amount of the partial pressure of the non-condensable gases. Two, instead of diffusing throughout the condenser, the non-condensables cling to the condenser tube. Thus, the condensing surface area is reduced, which also tend to raise the condensing pressure. Non-condensables can be removed from the condenser by forging. The forging operation consists of drawing a mixture of refrigerant vapor and non-condensable from the condenser, separating the refrigerant and discharging the non-condensable. Ammonia systems are commonly equipped with forgers, but the only other system equipped with forgers are the centrifugal compression system, which use low-pressure refrigerants such as refrigerant 11 and 113. 113. Okay, next na tayo sa evaporator. Halos similar yung ibang proseso sa condenser. In most refrigerating evaporator, the refrigerant boils. Yan, ito lang i-consider natin dito. And the tubes enclose the fluid that passes over the outside of the tube. So evaporators that boils refrigerant in the tube are often called direct expansion evaporator. So evaporators that boil refrigerant in the tube. Figure 16 shows an air cooling evaporator and figure 18 a liquid cooler. Yan. So, ibig sabihin liquid cooler, andyan yung refrigerant sa loob ng tubo. Alabas sa shell naman yung water. So, ito naman yung air naman dito. So, yung refrigerant naman nasa loob. Okay? The tubes in liquid chiller in figure 17 have pins inside the tubes in order to increase the conductance on the refrigerant side. Ito yung tinatawag kung may mga heat transfer tube. Yan o, inner pin construction. Check nyo yung mga sa may mga band. Wolverine, ano pa? Wolverine tubes. Marami yun. So next. Direct expansion evaporator used for air conditioning application are usually fed by an expansion valve that regulates the flow of liquid so that the refrigerant vapor leaves the evaporator with some superheat as shown in figure 18A. May mga catalog to. May mga technical data rin to mga evaporator. Mga tapon dyan na coil, serpentine, tapos may mga distributor kung ilang tubo yan. Yes. Another concept is the liquid circulation or liquid overflow evaporator in figure 18B, in which excess liquid at low pressure and temperature is pumped to the evaporator. Now, boiling in shell. So, ito yung evaporator. Nagbo-boil, di ba? The classic prediction for the heat transfer coefficient for full boiling of water at atmospheric pressure is shown in figure 19. The tests were conducted by immersing a heated wire in a container of water. The tests were conducted by immersing a heated wire in a container of water. So, tingnan mo yung mga heat transfer na book mo rin. Yung kay McAdams yan. Ito. Ito lang siya may topic dito ganito. Sa boiling issue na kinopya na lang ng iba. So, the test, yan. And the boiling regime, AB, the boiling is called nucleate boiling, where bubbles form on the surface and rise to the pool. The equation of the curve is approximately certain temperature difference and the heat. Yeah. The equation of the curve is Q over is equal to C times delta T exponent P to 4, where Q is the rate of heat transfer area, C constant, and delta T difference in temperature between the metal surface and the boiling liquid. Mahirap, no? Then, to write the equation in another form, divide both sides by delta T. So, Q over A delta T is equal to HR is equal to C times delta T exponent 2 to 3, where HR is the boiling coefficient of watts per meter squared Kelvin. The value of HR increases as the temperature difference increases, which physically is due to the greater agitation. The disturbance frees the bubble. The disturbance frees the bubbles of vapor from the metal surface sooner and allows the liquid to come into contact with the metal. Kaya ka, continue siya boiling. The rate of evaporation can be increased to a peak where so much vapor covers the metal surface that the liquid can no longer intimately contact the metal. A further increase in the temperature difference decreases the rate of heat transfer. So the graph in figure 19 is useful in predicting the trends for heat transfer coefficient for boiling outside tube bundles. Hoffman summarized the work of several investigators to provide the bind zone in figure 20. This is naman boiling outside the tube. Ito naman inside the shell. So para siya, para siya. Outside tube and inside shell. Ito naman yung ito naman prediction. So boiling inside tube. Where refrigerant boils inside this tube, the heat transfer coefficient changes progressively as the refrigerant flows to the tube. So ito na naman kano heat transfer coefficient of refrigerant 22 boiling inside tube curves 1, 10C, 2, 3C. Ayan. So ito yung fraction of liquid vaporized distance along the tube. So may distance pa. Ito yung heat transfer coefficient. As the refrigerant proceeds through the tube, a fraction of vapor increases, intensifying the agitation and increasing the transfer coefficient. When the refrigerant is nearly all vaporized, the coefficient drops off to magnitude applicable to vapor transferring heat by forced convection. So, yan. Sabihin, along the tube. So, mag-iiba-iba yung coefficient. So, isa-isahin mo yun. So, graphical na. Numerical methods. Figure 21 shows, 20. Ito yung 20. Ito yung by Hoffman. Okay. Yan. So figure 21 shows local coefficient throughout a tube for 3 different levels of temperature. The heat transfer coefficient is highest for the high evaporating temperature, probable because at high evaporating temperature and pressure, the vapor density is high, permitting a greater fraction of the metal to be weighted with liquid. Now, pressure drop in tube. The pressure of the refrigerant drops as it flows to tube type evaporator. In tubes. The effect of pressure drop in system performance is that the compressor must pump from lower suction pressure, which increases the power requirement. On the other hand, a high refrigerant capacity can be achieved if more pressure drop is transmitted. And this high velocity improve the heat transfer coefficient. Typical pressure drop for air conditioning evaporator are 15 to 30 kilopascal. So yan ha, pag nag-estimate kayo ng piping, so pwede mong i-average to or maximize mo para makuha mo yung tamang pump. Or the refrigerant pressure drop is sa pipe size. Okay. And sa carrier, meron doon pressure drop computation. Frost. When the surface temperature of an air cooling evaporator fall below 0 C, frost will form. Frost is detrimental to the operation of refrigeration system for two reasons. One, thick layer of frost act as insulation. And two, in frost convection coil, the frost reduce the airflow. Nabara. With a reduced airflow rate, the U value of the coil drop. And the mean temperature difference between the air and refrigerant must increase in order to transfer the same rate of heat flow. Both these factors penalize the system by requiring a lower evaporating temperature. Bababa. The numerous method of defrosting are available. Yan, i-defrost mo lang. And probably the most popular ones are the hot gas defrost and water defrost. Yung hot gas o water defrost naman, yung buga man tubig para mag-melt. Yung iba naman is electric. Yung iba, nabalutan ng defrost heater, electric defrost heater, yun. Pero mostly is hot gas. Yung sarili niya, sarili system niya kumukuha. Okay. In hot dip gas defrost, discharge gas from the compressor is sent directly to the evaporator and the evaporator performs temporarily as a condenser. The heat of condensation melts off the frost, which drains away. In water defrost, a stream of water is directed over the coil until all the frost is melted. Yan. Okay? So, yan ang topic natin sa condenser and evaporator. Yan. Sa ilalim, taas. Ito ngayon ang uso eh. Kasi yung nasa ibabaw nalagay nila. Ito yung uso ngayon. Sa ilalim, pataas. Yung fuel sa baba. Kita nyo. Okay? Thank you very much. Tagal mag-off. Ay. Yun.